All right, how we doing today? Good, bad. We just had an exam today. Uh, Dr. Pushkins, and you guys went over RLCs, right?
Yeah, I had all everything. RL, RLC series, and parallel.
And then let me see. That's what I was trying to look up here too. Let me see. Let me see what notes he gave you guys. Because he said you gotta brute force these equations and memorize them and have fun. No questions asked because you don't know how to do. Think was it differential equations? Second order ODEs. Let me see if I can show you what I was trying to do. See, now I got to do this, by the way. I got to move on like that. And then let's see, solutions. What do you call it? RLC circuits. This is the chapter, right? Let's see, what else can we talk about?
Where's the more that you just saw? He posted the solution now, so we can try to reference one of the homework and then we can do the solution for you kind of take the proper.
Yeah, so I was looking at these, what do you call it, notes as well. And one of the things that I feel like some of you may understand, because I had a gentleman just say, well, what the heck is going on? And that's based off the governing equations, right? Let me see if I can zoom in. Yeah, it was this governing equation, your second order equation, where if you solve for the auxiliary equation, and let me show you what I mean. I'll show you. Gosh, I don't like this format. Ugh. They updated the SEB thing. So if you're given the following general equation, I don't know, x, should I use x? And I'll use y double prime plus, what do you call it? A y prime plus b y is equal to, I don't know, some 0. I'm just going to put that there for now. So this is your general second order equation. If you're going to see this a lot in all your classes in electrical engineering and probably computer engineering, not much, but responses, because you want to know what your system does. That's the whole point. Your microcontroller, it's going to, when you have a step response, you're going to see the ringing and you're going to be like, what the heck? I don't want a ringing in my circuit. I want, like, what do I mean by ringing? When if I have a step response here is 0 volts, right? And then you'd ideally want a 1 volt, right? You want a straight square, right? Square. But sometimes your microcontroller does the following, where it just does this. You get these ringing things right here. That's your, what do you call it? It's like resonance, right? Where the period between, let me see if I were to show you this. The period between this and this, like this distance right here, is your resonating, like that period, right? Or F naught, right? There's going to be some resonance in that, and that's where you're going to look at overshoot or yes. Termination resistor? Say that again? Wait, I'm sorry, I can't hear you. So without termination resistors, are you talking about reflection coefficients and signal lines? Well, you won't know about that. You do. Basically, if you have some, if I were to show you some wire, this is some wire, certain pipe, right? And you see this all the time. If you had like a bouncy ball, or here's your electrons, right? They're traveling around. Let's just say you're trying to do this corner right here, right? You know these electrons, they're going to just bounce around in these pipes, right? But some people are trying to build these types of wires where you have this kind of reflection. So you have your electrons just going this fast, current I, right? But then sometimes there's a chance where, yeah, the electron's going to go this way, right? But there's going to be a chance where you're going to have some reflection coefficient. so that you're going to see some of the signal come back. And ideally, what we want is for all the signal, your transmission, your actual current to go all the way through your system. So this is like point A to point B. And if you wanted to do some two-type terminal, you'll see it as this is more like introduction to like S parameters, but I don't want to get too complicated. But is that what you're talking about?
Yes. And one thing we do, have you ever ran into the PCI bus?
A what?
PCI bus on computers, have you ever run into that?
PCI?
Yeah, scanner, bus scanner.
Scanning?
It's a standard.
Standard?
Yeah, it's one of the bus scanners. It actually uses the reflection.
Oh, PCI. Okay, that's what you meant.
At the end of the, it doesn't terminate, and it actually uses that reflection to pull it on the rest of the way.
Yeah, so
It's really long.
one of the things I know, and you'll see this in, we have a special PCB design class. Well, there's the practical one in the labs, and then there's the other one that I think Dr. Harris teaches. I think she's the one who does high-speed PCB design. What do you call it? There are standards for those types of reflection coefficients, but if I were to tell you this, and will you necessarily see this? Maybe, I don't know. So you're gonna have some type of source right here, right? And it's gonna be on some, I don't know, if I were to draw some line, some transmission line. Right, some transmission line, and it's gonna travel to the point where you're gonna have some type of load. Okay, and this line itself is going to have some type of impedance, so think of like a coax, for example. If I were to do like some type of coax line, and then you have your signal here, here's your copper signal, right? That's in the middle, and then you have some type of like bushing, right? Some bushing, which is basically like isolation.
Is that like the little piece of it looks almost like aluminum foil that they put on the outside?
Yep, that's what it is. And then you'll have some like, I don't know, another, what do you call it? Some other foil around here, which can serve as your ground. All right, if you don't know what I'm talking about, this is what it looks like. Oh gosh, I had to do this mouse thing. Let's see. Oh, what the heck? Yeah, they've updated this thing. Coax, cable, internals. Let's see. Stuff like this, you see. Oh, no. Elcom. Elcom is a good company. Well, I bought some stuff from them. But let me see. Oh, gosh, I hate this thing. I'll see it like this. This is a good picture. Yeah, you get the conductor. You got some insulation, right? It's going to be whatever that's going to cover your signal itself. And then this shield right here is your ground. So if you think about it, your transmission line is consistent of like some type of, if I wanted to really rewrite this, you can do like some resistors in there, some R, like parasitics, whatever, or some, this P is going to be confused, whatever. And then if you know that transmission lines, they also have some type of inductance right here, LP or something like that. I don't want to use L's or P's. And then you're going to notice that because you have the form where you have the signal right here, right? Your signal is traveling through this wire, right? And then you have the ground plane, right? This is ground, correct? You're going to realize that you're going to create a capacitor between this. So if I were to do like this, like some mini capacitance in this line itself, you're going to get some type of line capacitance. I guess some people write it like, I don't know, like this. C, RL, RTL, or RL, LL, and CL. You're going to have this kind of like line. And this is just for like, I don't know, some impedance per like or meter square or something like that, all right? Per line, okay? Right? But usually for our coax cables and a lot of cables, usually that impedance has already been determined. where it's called the characteristic impedance, which is usually 50 ohms. That's usually our standard that we work. And the way, if you don't want this system to have any type of reflection, you'll have to have it to where your load is matched. Load to have about also 50 ohms, okay? So that's another way you can do it, so that all the signal just goes through it. So one type of load are those termination blocks. Let me show you. Is this it? There we go. 50 ohm terminator. Yeah, stuff like this right here. And this is good to put into your system if you're trying to not test that port. Because let me show you, if let's say you're doing some plumbing in your house, right? And here's you, okay? And here's your pipe. And then you have, I don't know, here's your sink, correct? And then, I don't know, you're trying to test whatever, I don't know, the main line, right? Your water flow, correct? So for this, the easiest way I can tell you about termination is like, if you put a termination, you have to terminate it, all right, with some type of block, so that when the water flows, if you're analyzing from in to out, that all that water, you're just measuring whatever's in here, because if you don't terminate this point, you're gonna get to the point where stuff just starts leaking out here. If it's an open or if it's a short, it just goes right through here, and you don't want that, okay? So that's why they tell you to always put these little term blocks. I know they're little funny guys, but what do you call it? Let me see. There we go. These little guys are pretty tiny. I don't know if there's a good way to show you. But they're very small little guys, but they can get expensive. You want to see how expensive they get? $42, $32, $132, and they're tiny little guys. But they're really helpful when you're trying to calculate the the full transmission of a signal through your system. All right, is that good? But in the terms of what we're talking about with reflections, I think there's other terms, like you'll learn about voltage standing wave ratios, VisWar. That's a great word. You'll learn that in electromagnetics. And but in the terms of this class, I wouldn't worry too hard about it. But you're onto it. Let me see. How do I get back to my screen? This transmission line will be dependent on what your load is, because there's an R, there's an L, and there's a C. You have to match it so that all of it is like it's a perfect signal. All right, does that make sense? So yeah, that's leading into it. But right now we're learning all the brute force math of you got to know about this resonance and how to deal with it and how to make sure your microcontroller are all stable. Okay, so does that answer your question somewhat? All right, anyways, what's our next question? What were things that Dr. Pushkin talked about in class, or what do we want to go over?
Out of curiosity, David, I know like coax has been used like widely so much, like huge. You know? And now we have fiber.
Yep.
So are they trying to phase out coax, or do you think coax is like something that's just going to be around for a very long time because of like its functionality?
Well, coax is pretty nice. Honestly, it's reliable. It's pretty chill. I like it. But the thing with fiber is you can definitely fix it. But once you break it, then
that's over.
Kind of, I guess. You just need to.
It's hard.
You just gotta fix that point so that you don't have any reflections. So the way that optic works is, if you think about it, optics, and this is like it's basically glass. Glass right there, and you're literally shining light into this little tunnel. So there's a theory, and you'll learn this in electromagnetic transmission line theory or optics. I know Dr. Shiguyev is one of those professors that master that, where you'll notice that the wave is just going to start like reflecting inside to the point where it's not going to leak out. These fiber cables are just designed so that the signal just stays in, okay? But if you have to the point where there's like some type of like, I don't know, some kink into like I don't know, some kink or bend or crack and you try to use like some signal, like what do you call it? What do you call it? Not signal. It's a vector network analyzer. You can do some S parameters, okay? So you get S11, and then you can measure this actual voltage standing wave, because you're going to get to the point where this signal might reflect a little bit of it back, okay? That's what's happening in your glass. So the point of this is to avoid this at all times. The coax is more forgiving because it's just wires and copper conductors, not too bad. But with glass, it's you got to be careful with it. So I don't think it's going to go obsolete. In fact, it's really nice to have. There's coax cables. There's lots of other. It's not that bad. So does that answer your question?
Yeah, I was just curious.
Yeah. So there's many other wonders in electrical engineering. What else? What's his name? But yeah, fiber is pretty good. And then if you really want to go deep into it, you'll realize that. Has he talked to you about AC analysis?
We talked a little bit about it.
Okay, so let me just show you some quick terminology. Can anyone agree that if I put let's see, how do I want to show you this? If I put what do you call it? 1 volt here, right? And then let's just do, I'm going to do, I don't know, 10 volts? Yeah, 10 volts, whatever, right? And if I were to, let's just say, if I do the voltage divider, right, this is R and R, right? If it's the same voltage, right, what's the voltage over here? Without thinking. Come on. Come on, this is the easy question. I'm going to put this on my final exam.
That's just I over R.
What's the
Oh,
voltage?
what's that?
If I have
You have 10 volts.
so if I have 10 volts here, I have a resistor here, I have another resistor here. This is a good 2-pointer question. It's a voltage divider, right?
Yeah.
So what's the voltage? 5. It's a half divider. Because if we have the same components, it's just going to divide in half, right? So what I was trying to get to you guys is there's a special, well, it's a more passive circuit. You can try this in the labs. Go ahead, be my guest. Where, let's just say I have a frequency, and I'm just going to do like some funny sine wave, okay? This is like, I don't know, 1 hertz, okay, right? And then let's just say I wanted to do, I don't know, 10 hertz signal right here, right? And so that means it's just oscillating like this, right? It's a really fast sine wave. You can do the following, where you can mix them into one point. And then if I have this resistor right here, R, and this can also be, let's call it RR, right? Where this signal right here is just going to be adding these two signals. So you're going to get, what do you call it, F1 plus F2. Well, this is a voltage divider. This is the voltage itself, R divided by R plus R in parallel with R. Okay, 1, 2, L. Okay, R load, 1, 2. Does that make sense? What I'm trying to show you right there? Simple voltage divider. Is that good? Did I lose anybody right there? So okay, so you can send many signals and you can mix them, right? Mixing, okay? You can mix signals into this little pipe, right? And then you wanted to build some type of filters, right? And well, you guys don't know that until you go really deep into 221, where you get to the point where you have, you can analyze this in terms of not just the time domain, but the frequency domain, right? And you can have like channel, I don't know, channel 1, channel 2, and channel 3. And you can just build these cool little filters, like, okay, I have 3 channels on one pipe. So I can just build like filter 1, filter 2, and filter 3, and just you can do this just with a tuner. So that's something you can do too. So that's communications at UNLV 460. I think the prerequisite for that is 360, which is what I do, signals and system theory. So if you want to do more of that, be my guest. So I think maybe today might be the fun lecture where we're just talking about the discussion. Okay, we're discussing. So, you guys took an exam. Let's take an easy day. So this,
when is that?
huh?
Your discussion?
Oh no, this. Oh, what do you mean? So I have a discussion. This is our discussion right now. So we're just chilling.
Oh yeah.
Okay, but I have another discussion. But funny enough, I made a video for that, so we're canceled for tonight. Okay, y'all.
Oh.
If, people still watch my videos. I don't know why. Well, they like it. I don't know.
Do you post them outside of Canvas?
They're all on YouTube.
They're all on YouTube already?
His little module, you can look at all of these.
Oh, that's cool.
Yeah, well, yeah, because I guess some people didn't understand that. Because yeah, I embed them, but it's a YouTube embedder, so you can use YouTube. So,
Oh, okay.
and the complaint was, well, it wasn't a complaint. It was someone saying, I don't like, what do you call it, NC Okta, the verify, and they're like, I hate this. So funny enough, I didn't even do it because of that. I just have YouTube Premium. I don't know. I gotta love my no ads. Watch my Signal Theory.
The two-factor thing on Okta is ridiculous because I run two-factor on everything,
Two-factor, yep.
but it doesn't even save the login for more than about 2 minutes. So I have to constantly put the code in.
Yeah, I agree. Yeah, it just does some weird things. Back when I was here, 2016, did we have? No, we just had the good luck. Remember my password, and it didn't even log you out. It was great. Well, unless someone like hacked you, and you're kind of done for. So, yeah, I guess you had the extreme of now you have to use the Okta stuff. But anyways, this tuner stuff right here, you can learn this in like filters. It's like filters. Communications, and then maybe, I don't know, signals and systems. So like this right here is EE460, right? And then this right here is EE330 and 430. And then this right here, well, this right here is just circuits, okay? So what other classes do we have? And then actually, better yet, if you wanted to know about power matching and the transmission line stuff right here too, you can learn this also in your, what do you call it, 330. We also have our EE340 class, which is our power class, which focuses on, what do you call it, the actual reactive power. You have real power, you have reactive power, which is volt amps or VARs, right? So it becomes a pain. But anyways, and then material sciences, and well, this is a special PCB class if you wanted to take that. So anyways, which is page 3. So you see how there's so many fun things you can do in engineering once you pass that threshold. So what's his name? Let me grab another piece of paper. This is page 4. But yeah, what else is there? So resonance. So another thing about resonance, if you really wanted to get deep in this, you'll notice that you'll have some poles, right? Let's see if I were to do, oh yeah, I'm trying to tie this all back into this original thing that I was trying to do, okay? Where if you get the characteristic equation, you can rewrite it as lambda squared plus a lambda plus b, right? It's equal to 0, correct? To where you can solve for lambda is equal to the funny song, which is negative a plus or minus the square root of a squared minus 4ac, so it's b, and then all over 2, right? Okay. So all those weird equations you have to memorize are based off this guy, okay? You can get 3 types of conditions with this. The condition where if you're looking at just this term right here, where if a squared minus 4b gives you a result where, what do you call it? The a squared term is bigger than 4b, right? If this term is bigger than this, then you get the classical, oh, you get real components. It's not that hard. You get a real value, okay? But then there's a condition where you have it to where the negative 4b, so the, what do you call it? If I were to do 4b, right? the magnitude is greater than this, okay? So now you get an imaginary number, right? Right? So then that's when you have to start using those other equations. So all those funny things you had to memorize, which was, let me see, God, I hate this new thing. Let me see.
One of my classmates was showing me a calculator that does imaginary numbers.
Yep. So it's right here. See, here's your, well, that's your general equation, okay? Let me see. Over damped, and this is greater than that. Middle to the right. Total solution, yeah.
That's easy to remember.
That's what we used to do. That was
Yes,
yeah.
That's all everything. Easy,
No.
that's everything times t solves everything for
Yeah, so basically all signals can be defined as this, and it's not that hard, okay? And then suppose it's not an exponent, right? And now you get, so this is a real number, right? This is going to give you some real values, okay? This, what do you call it? This equation right there. So now let's get to the condition to where, let me see. It's all that funny quadratics. Let me see, where's the other? So you get the condition where, what do you call it? Let's see. Alpha is equal to omega naught. Let me see. So, okay, let me show you what I was trying to do. So this imaginary case, right? You're gonna get some value. It's gonna be like, I don't know. So someone's gonna get mad at me for doing this, plus JQ or something like that. Okay, you're gonna get two poles, plus or minus. Okay, something like this, where your what do you call it? Your lambdas are gonna get, you're gonna get in a complex pole. Okay, so that means you're gonna get some sinusoids. All right. Okay, and that's something you gotta know. So now there's a case to where you have this term right here, right? A squared minus 4b, right? What happens if it just disappeared? So now it just equals 0. So, all right, it's gone. So now you get to the point where, well, lambda is equal to minus a over 2, right? But I need two solutions, right? It's a quadratic equation, right? I need two solutions. Is that two solutions? No, I need to pop another one. So when you're doing your general guess, you're going to do, ce to the, I don't know, st, right? Or t, yeah, tau, or time, right? Plus, we're going to do another guess, okay, too. I'm going to multiply this thing by t, and then you get e to the st, all right? Is that what you guys have to do? Right? No, it wasn't there? This one? Let me see, because that's what I was trying to do. The point where, let me see, this just looks ugly. Yeah, there it is right here, you see? Oof, I memorized my equations. Let me see, where'd it go? This right here, it says for, what do you call it? The condition to where, let me see, where's my visualizer? This term just disappears right in the quadratic, right? Okay, we're remembering quadratic equation. It's gone. Now you need a second pole. So we're just going to create a second guess, okay? Because if you try to copy and paste this, that's not going to work. You're going to have a double pole. This is considered a double pole. All right? So you have two poles that are on that same, like characteristic root, okay? This right here is also like two poles, but they're conjugates, okay? And then this right here, well, you have a real pole. They're really nice. They're pretty simple, okay? So anyway, let's see. Is that making sense what I'm trying to say? Or am I going too fast, or is it going too hard? I don't know. You let me know. So yeah, that's when this condition here happens is when you have to use this equation. All right, and then let me see, where's the oscillations? Here's the oscillation right here, right? To the point where you have a real and imaginary component. There it is, yep. Some ugly little alpha j omegas. Get this, you got that. And then you can technically write the answer like this and you'll be going home pretty happy. But we got Euler's equation. Euler's a really nice guy. He says, well, I love Euler's equation. I'm an exponential person. I like that. But if you like trigonometry, that we can do that too. Cosine plus j sine, okay? J sine theta. To where you can rewrite this into this ugly mess, all right? And then you got to memorize it, and it just becomes painful. Or, see, that's why I like Euler. Everything becomes simple. Let me see. How do I want to show you this right here? Put that there. So if you really wanted to, you can honestly brute force every problem using this kind of like format and then understand the characteristic equation. If that's okay, so this one right here is going to be like y is equal to c1 e to the I don't know, s1t, right, plus c2 e to the s2t, correct? Very simple, all right, because it's real. Okay, it's real. This is imaginary, all right? So you're going to get to the point where you get the same thing right here, but your s's are going to be real plus j imagined. And it's going to be plus and minus, okay? Conjugate poles. And then this right here, well, you have a double pole. You have two poles that just exist, and you can do this, but you need to add a t. Add t, okay? Is that good with everybody? Or does someone want to make a super hint to what we're trying to do for the next class or next semester, which is Laplace? Have you guys talked about Laplace?
He mentioned it, but he hasn't used it directly. He mentioned it indirectly.
Yeah, just briefly.
So I'm gonna go crazy on you guys. Laplace. So where this is gonna be super crash course, but you want your poles to be on this left side, right? So if I have the condition where I have, I'm giving my 360 students the answer: c1 e to the s1 t, right, plus c2 e to the s2t, right? You can write this in terms of, what do you call it, ys, right, is equal to 1 over, or not 1, c1, 1 minus s1, right? Where the pole, no, s1 minus whatever that is, or pole, or pole, I don't know, I'm just writing something, okay? Where S1 has to equal that pole value, okay? Is that good? So what I'm trying to show you is you can do the following: pole 1, P1, and then P2, and boom, you're done, okay? Easy Laplace transform. This is going to give you two squiggly sine waves that are going to do the following in the time domain, okay? It's going to do this. Oh, yeah. Or not that, sorry. They're real. It's just going to be whatever. It's just going to be resonance, okay? It's just going to do that. Exponentials, okay? But now what happens to the point where you have a pole system like this? Here's your Laplace transform, L of S, okay? Where your pole looks like this and this, okay? P1 and P2. This is the real axis, and this is the imaginary, right? So I have some real value right here, right? R, right? Real. And then this right here is like my plus imaginary. And this right here is my minus imaginary, right? Is that making sense what I'm trying to show you guys? So if you wanted to, I'm cheesing this, y'all. C1 e to the, what do you call it? Minus R plus J imaginary, right? T, right? Easy. Plus C2 e to the minus R plus J imaginary T. All right? Two sinusoids. Boom, done. Go home. Is that cool? That's what we use the Laplace transform. Stuff just goes. Life becomes easier once you memorize how to use this tool. Like, to be honest, electrical engineering becomes a lot easier when you memorize this one. So, and then you can make, I don't know, 6 figures and go home and not do anything. Anyways.
Just with that, huh?
Yep.
Just with that.
Then you got the case where you have the double pole, where it's like double pole times 2 right here, right? Well, how do I describe the first pole? The first pole is easy. We'll see 1 e to the, I don't know, minus RT, right? But I have a second pole. I just can't do plus C2 of that, right? That's where you need to do C2e, or what do you call it? TE to the minus RT, or whatever that is, okay? That's where you have to consider this double pole, right? So this is intuitively using the Laplace transform, all right? Is this clearing you guys up to like, man, this homework is tough, man. I don't want to do it anymore. But anyways, are there any questions about what I'm trying to explain? Yes, no, maybe. Anyways, what other stuff did he go over in class? And by the way, yes, all this stuff you learn in E360. Okay, that's what I do.
So you don't learn Laplace transform?
Oh, you also do that too, but Math 431 also does that. Math 431, and I guess you need this plus EE 221. You'll learn the theories in these two classes, the first two, but you'll practically have to apply the Laplace transform to understand anything going on. All right? What other stuff did he go over? Let me see his notes. I'm not liking this computer, how it's working. Anyways, let's see. Because once you understand Laplace transforms, if you can describe this first part, memorize this point right here, and just ignore this part. Let me show you what I was also trying to say. Because I'm just doing like intuitively, just helping you guys think. Okay, let's go back to my screen. So you'll probably come up to a plot where, oh, here's my voltage, right? And we're charging, right? Hooray, right? We're doing something, but something in the circuit switches. Switch. Did I spell that right? Yeah, switch. Okay, right at this point, okay? And we're doing something to describe that. How do we solve this problem? Well, so this right here is our t is equal to 0, right? Right? But if you think about it, if you just start something like this and just cover this part to the point where, oh, here's my v t nu, right, is equal to 0 minus, right? If you start thinking it like this, you'll get some charge, okay? Some whatever voltage was there, all right? If you memorize that, and you can describe a new equation to get you some other thing. You're going to get some delay, all right? In fact, this is going to be add delay, okay? And then you have whatever this e to the minus, I don't know, st or whatever your pole is, okay? Is that cool? Yeah, so basically you can describe any system using Laplace transforms. Well, in analog cases. In digital, you'll have to go to the Z transform, which is a EE480, our digital signal processing class. So you see how, yeah, the hard math is going to suck right now. This is why we need to get you guys, it's practice, memorize, or not memorize, but, well, understand where it's coming from. I'm showing you that right now. If you wanted to do some more research about second-order differential equations, you can. And then you'll understand, because if you already knew differential equations, then let me show you right here. Then where's that funny table? This table. Some engineers probably got it tattooed. He's like, yep, I got this. But for you, it doesn't make any sense. But once it makes sense, you'll be like, I like your tattoo too. So is that making sense what I'm trying to say? So for me, when I'm looking at this, for the first few seconds, I'm like, what the heck? But once I understood, I'm like, man, I memorized this table too. I'm not doing that math. But for you guys, you're just plugging and chugging. What the heck's going on? Okay? Auxiliary relations, and then parallel circuits, and then that's pretty much it. So And then I guess he's throwing you into the, what do you call it? AC domain, right? Is he doing that yet? Okay. Let's see, page 6. So I'll show you one thing. And my signals and systems students, well, now they're masters of convolution. Well, what's his name? I want you guys to know this too. So, my circuits, right? It's your happy circuit, okay? And here's your x of n, or x of t, y of t, right? And let's just say if I were to put, like, I don't know, some DC signal right here, if it's like a pulse, right? Right? What do I get out? I got out that same pulse, right? Right? However, this right here, your circuit, it's got its own transfer function, okay? H of t, there's some impulse, okay? It's doing something. So this pulse is going to be multiplied by whatever magnitude, all right, plus some phase or distortion, and distortion. Okay, so this is the general gist about how AC analysis is going to work. You throw a pulse in, you're going to get some pulse that's going to, like, the magnitude is going to go up or down, and it's going to be delayed by some function, or the frequencies are going to be delayed, all right? So the square might come out like, I don't know, it's maybe if I were to draw this like this, here's our impulse, here's our signal coming in, right? Like that. That's our V in, right? But then V out might do something like this, where it comes out, but it does something like this, a little ring, and then like that, right? And then if I were to try to, and then there's a delay right here. Let me draw this delay. All right, is that good? And then this term ringing or resonance. Okay, right? And then if I were to keep going, right, and if I go down, you'll also see that same pattern where, oh, and then it just does this. Okay, that's what you're going to see in the labs. All right. So what if I just did the following? If I threw in a squiggly sine wave, okay? It's a sine wave, right? Sine. Right? What's going to come out of the system? A squiggly sine wave. Yeah, it's just whatever. Yep. Times some magnitude, and then plus some phase. Okay? So then you'll get to the point where, oh, here, I'm going to do it again, okay? And then here's your good old sine wave, right? Just does this, right? And then you get to the point where, oh, maybe your thing is going to do the following, where, oh, it doesn't start until, like, well, at that point, it'll just start like this, and maybe it'll just do this. Am I getting that right? Boom, boom, and then like that, okay? There's a delay in there, and you're going to have to figure that resonance out, okay? And then, well, there's no resonance here. If you wanted to mimic a resonance itself, like let's just say this is resonating, frequency naught is equal to, I don't know, like 10 hertz. So if you were to analyze a system that, oh, it likes 10 hertz, this system really likes ringing at 10 hertz, and if you give it 10 hertz, you're going to realize the gain. Let's say if I were to give it, like, if I were to do it again right here, T. If I gave it 10 hertz, right? I'm just drawing some signal, right? V in. And then my resonance is just going to go crazy to where it's, well, it's not going to be 1-to-1. It's just going to be, would it be 180 degrees? I don't think it's going to be 180. Well, it's probably going to be, you're going to get some type of amplification where it's just going to be big nations. like you're gonna get some type of oscillations in there. Okay, it's just gonna be a big amplification signal. All right, so if you give it the frequency that it's ringing back at you, like antenna theory, then it's gonna respond with that signal. So have you ever played with what do you call it? It's like these like tuners, like these like metal tuners, like that make a pitch, right? Have you guys heard of those things or seen them? Yeah, like what do you call it? Uh, huh?
Like a network tunnel?
Not that pitch.
The way that those work is the,
Not that. There, what's these things? Yeah, these tuning forks. Yeah. So like, if you sing into one of these, right? If you hit it, it's gonna make a sound, right? That's its resonance. So if you sing back at it at that same pitch, it's gonna sing to you back. That's what I meant by that's what I mean by this condition right here. To where is it? If you give it what it wants, right, 10 hertz, it'll sing that pitch, and that may be good for if you really wanted to like encode some signal on that line, okay, and then everything else can be filtered out. Does that make sense with everybody what I'm trying to do? Anyways, are there any other questions regarding, I don't know, anything? But yeah, this is like basic intro to AC analysis. I'm not going to go really too deep because the other things you'll realize is that there's going to be some delay, right? And then you know that because sine waves are a circle, right? If I were to draw a circle, 0 degrees, 90 degrees, this is 180 degrees, right? And this is 270 degrees, right? You'll notice that, well, you have to, what's the delay? If this right here were 0 degrees, or not 0 degrees, this is 0 degrees right here, right? What's this in terms of degrees? Okay? Does that make sense? So like if I were to go here, that's 0, this is 180, this is 360, right? So with reference to this signal, right? What is this? What's the degree of this point right there? I don't know. If it were like right here, right? That's like, this is 90 degrees. Yeah, that's 90 degrees.
No, so that's a 45-degree delay, right?
Huh?
Like, because it's half of it, like 45-degree delay.
Yeah. Well, this is half right here. This is 180, right?
Okay.
And then this right here is, what do you call it, 90 degrees. So if it was, yeah, I guess I drew that wrong. But anyways, I'm just trying to tell you what you guys got to prepare for, okay? And then basically all you're going to do in 221 is just analyze this, okay? And then, sine waves are cool, but you can also do pulses, and you'll see a magnitude and a phase, or aka the delay of the signal of your system, whatever your circuit is, okay? And then what is H of T? Your impulse response. You're going to study that in 360, okay? So now you really want to deep dive into what your circuit is truly doing. Then you can model it in the computer, and then you can just never have to build circuits ever again. You can just throw numbers at it, do some Monte Carlo or whatever you want, and have some fun. So anyways, that's a 360 concept. So if you're in the electrical engineering domain, you're going to understand what this is. And if you wanted this to be like AI, machine learning, you can tune this to where this is a function of its output, and you have some error signal like, oh, I feed this back into the system by some type of weight. You can change your impulse response, and stuff becomes really cool. That's our graduate level courses, by the way. So you see how all this is connecting? What everything I'm saying, by the way, is probably going to be like, whatever. This guy's like going on some tangent. But no, I see this even in my, like, what do you call it? All the other people I've directed for the labs, for the grad students and everything. So I'm just giving you guys a hint on the beautiful surprises of EE. And well, CP, I can't really say much, but you can do some simple fundamentals. It's not that. What is CP? You just code, just program, debug that microcontroller, embedded systems, not that bad. So, are there any other questions for
Not particularly this, but I guess specifically, what's like the 420 back then?
420? Wait, say that again?
EE 425.
Yep. What about it?
No, can you give a brief general description? Is any of this proposed in that?
So, okay, so this is where the, I guess, the final pillar of circuits ends. And that's where, okay, I want to build some really cool circuits and go deep. And this is where I specialize in IC design. Which IC just stands for integrated circuits, right? And then you're like, okay, you know these like simple circuits, right? Yeah, we can build these in components, right? But what if we want to like size this down to like 45 nanometers, like really tiny technologies, or whatever Apple is doing and Intel, right? Like, is Intel doing like some, like, I don't know, is it like, I don't know what they're doing, plus 10 nanometers or 7 or, right? Yeah, but okay, here's the funny thing, because I've seen what they've done. It's more buzzwords than it is actual like engineering. But in reality, this right here is going to be known as like some kind of gate. What do you call it? Not gate. It's more like some gate. This is our gate feature size. Where you can start building transistors. And transistors are what you're going to learn in EE 320. Okay, you're going to learn about transistor theory. So you got your BJT, right? NPN. I guess that's how you draw it. It's one or the other, whatever. So you have your transistor right here. This is a NPN plus to minus. Yeah, NPN transistor. And then you have your MOSFET. This is where I'll be taking the directive to show you guys what we do in 420 lab. Now, the lecture is going to be by Dr. Zeus, so he'll do something cool. To where, okay, this right here is, I'm going to call it like some NMOS transistor, right? The gate right here, this right here is called our gate. And this is what is our feature size. That's what we're talking about, 45 nanometer processes. So if you wanted to build this circuit, you can. We just go into like really tiny details. So if I were to show you something cool, let's see. Oh, let me see. CMOS. Oh, CMOS EDU. Where's my stuff? This is my 360 page. Let me show you. That's me back when I was a good old happy grad student. And then let me see. Yeah, this right here is a chip that I was designing. So it gets pretty cool. It gets pretty fun. Let me see. But yeah, this is something I've done for the university. It was a 6-month project. I had a team of like 2-3 engineers help me out build this little chip. If I were to show you, this right here is a 180 nanometer process, but I don't know if I can zoom in. Ugh, this thing's so buggy. Yeah, like stuff like this. These are like fingers right here. They're pretty tiny. These little green guys. Let me see what else. But let me see. Transistors, IC design. There we go. Yeah, stuff like this. Oh yeah, this right here. Ew, is this Magic? Yeah, ew, I hate Magic. Magic is a free open source software. You can technically start doing IC design. Yeah, that right here is our gate. You see this length right here? That's our gate because our electrons are just going through it. So anyways, let me see. And yeah, we got some other cool stuff going on there. This right here is some transistors. That's our gate size. And then this is one like what do you call a rage bait video out there that's like showing you what an IC is and it's going crazy. But yeah, this is what 420 I want it to be, and we're going to be using Cadence, which is our IC designing software, so we can start designing circuits at that level if I were to show you something else. I don't think I can show you anything deep about it. But anyways, is that good? Are there any other questions? Yes?
I looked it up. The current high-tech gate pitches are between 40 and 50 nanometers with the interconnect pitch of 23 to 32 nanometers.
Yeah, I see. Everyone.
3 nanometer class.
Yeah, everyone's still stuck because we're never gonna get truly to like when they talk about 4 nanometer, 3 nanometer. Someone said like plus like 7++ nanometer. I'm like, this is just HR buzzwords or.
Yeah, you're not going to get any smaller because there's not enough electrons at some point.
Yeah, you're not gonna get to that. In reality, we're engineers. Okay, we're here to make stuff work. So okay, 49 nanometer process, whatever. Okay, not that bad. But when you hear these like 4 nanometer processes, that's just like to like milk the government or whatever. Like, hey, give us money and then we can just go on a vacation.
But it's 3 nanometer class.
Class, yeah. You see, they call it class, but then when you say what's your feature size, they'll be like, oh yeah, 40 nanometers. I'm like, then you're not at 3 nanometers.
No, it's 40 to 50.
Yeah, you see.
What anyone's doing.
And then what's his name? Let me see. Intel transistors under microscope. This is what I want to show you guys. Like these are all. Oh yeah, this is the thirst trap one. I hate this video. It's like it goes like super zoom. I'm like, this is baloney. I'll show you a real chip in upstairs. I have a whole bunch of them. But yeah, you see something like this. You see, it looks pretty cool. You can see it from it like this, and this right here is our wire bond connects to our pins, and then you go crazy with these are our transistors. That looks like some memory blocks, some whatevers. But yeah, this is what I want to try and do in our 420 lab. We're going to build some cool little, not chips. I want to see if we can get a $10,000 chip, but I'm not so sure because it takes like a year to manufacture. But we'll do some current mirrors, differential amplifier. We'll build an op amp. You can design your op amp, okay? And then here's the final note before we all go home. Op amp LM741 IC microscope. Is anyone gonna let me see? Yeah, you see inside the 741 is that IC. You can build this in Cadence. So those little black chips you guys saw, LM741 op amp, you'll be playing with this in my lab next semester. Unless you don't take 221 next semester. This little guy, okay? Is that cool? And then, oh yeah, here's the schematic. LM741 schematic data sheet. Boom, you already have the answer. You can build this in your Cadence or LT Spice and whatever and get it fabbed, all right? Is that cool? Anyways, any other questions before I leave? Have a good day, everyone.